We are now ready to put the finishing touch on our proof of the optimality of Huffman codes. We just proved the extension lemma here, which said that for any PMF in descending order, any PMF P, if P prime is the PMF obtained by adding the last two elements, then the H extension of any optimal code for P prime is optimal for P. And we had our earlier remark, which was that any Huffman code for P is the H extension of a Huffman code for P prime. And we're going to use these two results in combination to do a proof by induction for the optimality. Now, I'd like to make a little clarification about this earlier remark. I was a little bit loose in my statement of this. So let's tighten this up a little bit, be more precise. So here we were always assuming that P was sorted. So this was pre-sorted. That was our standing assumption. It was in descending order. But we also made the convention, and when I stated this, I mentioned it, that I'm referring here to the Huffman code that it's obtained from this pre-sorted, or a Huffman code obtained from this pre-sorted P, obtained by combining the last two guys first. And let's refer to that to be completely precise. Let's refer to that as a standard Huffman code. A standard Huffman code for a pre-sorted P is when we combine these last two, n-1 and n, first. Now, any Huffman code for P, whether P is pre-sorted or not, is obtained by permuting the P's in some, so that they are in some descending order. That permutation is not necessarily unique, because there's not necessarily a unique way to sort them in this way. But any Huffman code for P is obtained by sorting them in one of those equivalent orders, and then doing a standard Huffman code, right? Whichever ones you're going to combine first, you know, those are going to have to be minimal. That's part of the Huffman procedure. And so, you know, just pick the ordering in which those are the last two, and then that Huffman code will be a standard Huffman code for that particular ordering of the P's. Okay, that was a bit technical, but I want to make this all completely precise. So we'll see where that comes in the proof in a minute. So now we have the theorem. At long last, we get to state our main theorem, which is that any Huffman code is optimal. Any Huffman code is optimal in the sense of having minimal expected code word length. So let's do the proof. So the proof of this. So it's going to be a proof by induction, and let's define the following statement. This will be, I'm going to call this statement star k. So the statement star k is that any Huffman code on a PMF with k elements is optimal. So this is the k element version of the general statement. So I call it star k. And now we're going to do the proof by induction. So the first step when you're doing a proof by induction is the base step. So our base step is, I'll call it base step. So star 2 is true. Star 2 is true. Star 2 is true. I mean, it's no need to consider star 1, because that would be a one element thing. You're never going to have that, a code for one element. But for star 2, so this is true. Why is this true? Because if you have P1 and P2, well, there's only one thing to do. You combine those, you get your Huffman code. It's code word 0 and 1, and there's nothing better than having one bit for each of your code words. That's the best uniquely decodable code you could have. So star 2 is true. And now we need to do our induction step. So let's do the induction step. This is the main part, of course. So we're gonna suppose, so suppose star n minus 1 is true, and we'd like to show that star n is true. Okay. So star n says that any Huffman code on a PMF with n elements is optimal. So we need to have some PMF on n elements. So let's let Q be a PMF on n elements. So it's Q1 up to Qn. And we need to say that any Huffman code, so we have an arbitrary PMF Q, and we need to take some arbitrary Huffman code, let's say, so let C be a Huffman code for, or Huffman code on Q. 4 sounds better. Huffman code for Q. It's the same thing. Now, so this is where that sort of technical remark I was making comes in. So I said that any Huffman code for a P, pre-sorted or not, is a standard Huffman code for some permutation of P, for one of the permutations of P in which the P's are in descending order. So now our unsorted P is Q. So if we were to sort Q in descending order, then for one of those ways, C is going to be a standard Huffman code for that permutation. So C is a standard Huffman code for a permutation of Q. Let's call it let's write it this way. A permutation P. P is not a permutation, it's a sorting. So for an ordering P of Q such that P is in descending order. So P has all the same elements as Q, but now they are in descending order. And now we can use our remark, which said that any standard Huffman code for a pre-sorted P, which now our P is the H extension of a Huffman code for P prime. So we know now this implies that C is the H extension of a Huffman code for P prime, where P prime is the usual thing that P prime is. We add the last two elements of P. Alright, so C is this H extension of a Huffman code. And what do we know about the H extension of a Huffman code for a P prime of this form? We know from the extension lemma that if we have a P in descending order and P prime is this thing, then the H extension to P of any optimal code for P prime is optimal for P. And by our induction hypothesis, we have supposed that any Huffman code on a PMF with n-1 elements is optimal. P prime is a PMF on n-1 elements. So the Huffman code on P prime that this C is the H extension of must therefore, by our induction hypothesis, be optimal. So by induction hypothesis, so that code is optimal, and therefore C is also optimal by the extension lemma. And so since Q was an arbitrary PMF on n elements and C was an arbitrary Huffman code for Q, then that proves star n, star n is true. Any Huffman code on a PMF with n elements is optimal. And this is our that does it. That's our proof by induction. So we have proved that Huffman coding is optimal. That deserves a big QED. All right, so this proves that's our proof of the main theorem that any Huffman code is optimal. Huffman coding is optimal. Now, so maybe let me make one clarification here in the proof. So I said that here I said let C be a Huffman code for Q, and then I referred to C over here again as being a standard Huffman code for P. And, you know, C over here has some code words. So this C has some code words W1 up to WN. And when I refer to C again over here, I mean, you know, take the same code words, and since we're permuting Q to get P, then permute these code words in the same way. So, you know, the code word associated with a given number is remains the same. So you know, the length of the correspondence between lengths and probabilities is unchanged. So of course the expected code word length will be the same. It's just sort of, you know, we're just, you know, here we're just permuting things to get the indices so that it's nice and neat, and we can refer to n-1 and n and not have to have like some arbitrary pair of indices. So that's all that's going on here with these permutations. It's just to make the notation a little bit simpler. All right, so that completes our long awaited proof of this optimality of Huffman codes. And let me make a couple remarks here about just some brief remarks. One is that to take this result with a grain of salt. So it is optimal as a symbol code or a variable length code, but that does not necessarily mean that it's the best thing to do, that it's always going to give you the best compression, because there are certain weaknesses of symbol codes, namely that they have to have integer valued lengths, which can cause severe inefficiency in the amount of compression that you can achieve. So just because it's optimal as a symbol code doesn't necessarily mean that it's the optimal of any possible coding method that you might choose. Okay, so that's one caveat to note. And I'd like to mention one other thing, which is that, so we showed that any Huffman code is optimal, and it's clear, it's fairly obvious that the converse is not true. So here's a remark, not every optimal code is a Huffman code. And it's pretty easy to come up with not every optimal code is a Huffman code. It's easy to come up with an example if you think about this for a minute. So here's one example, which is, since every Huffman code is a prefix code, then but you know, every Huffman code is a prefix code, but you can get an optimal code in terms of minimal expected code word length that's still uniquely decodable, but it's not a prefix code. So I'll give you an example of that, but actually let me save that for another video. So we'll do that in the next video. All right, so that's our proof of the main result of the optimality of Huffman coding.